2019. He worked in VIT AP from January 2020 to October 2022 as an assistant professor in School of Electronics Engineering. He served as an assistant professor in Electrical Engineering Department, NIT Jamshedpur from October 2020 to January 2025. His current research focuses on the areas of model order reduction and its application, fault detection and accommodation, and integrated vehicle health management systems. So I request Dr. Arvind Prajapati to take over. Dr. Arvind Prajapati. Your microphone is muted.
So thank you, sir, for your nice introduction, and good afternoon, everyone. So I'm going to present today's talk on the H infinity based robust control and problem solving. So these are the content which I will deliver in today's lecture. Like, we will first see introduction on the H infinity control, and then we will see like literature survey in the H infinity control. Then we will see what are the basic concepts related to the H infinity control, and then we will see problem formulation of H infinity control, and then we will solve the H infinity control by using like either Riccati equations or by using LMI's approach. Then we will see robust analysis with respect to H infinity control. Then we will also see what are the trade-off of H infinity control related to the robust performance and robust stability. And then we will see the areas where H infinity control is widely used. And we will also compare our H infinity control with the existing other controllers. And then we will also cover future scopes in H infinity control. So before going to learn H infinity control, I'm just going to introduce something which everyone is familiar, like ADAS. ADAS is what? ADAS is nowadays is coming in modern vehicles. So ADAS, what is the full form of ADAS? So I think everyone is knowing Advanced Driver Assistance System. So what is the work of ADAS? So it will detect if something is suddenly, some abnormal thing is happening around the vehicles, then it will automatically detect and do the action. The driver is running on the road and his front vehicles has suddenly brake. It tries to detect yes, front vehicles has done the braking, so I have to do. But if there is a ADAS in the vehicles, so ADAS will immediately judge, yeah, front vehicle is have some problem or they have done the braking. So it will automatically stop your vehicles if your vehicles is having ADAS. Similarly, suppose if you want to turn your vehicles right or left, and drivers haven't seen, yeah, someone is behind which he is coming from the left or right side, then there may be some accident may happen. But if there is a ADAS, so ADAS will detect, yeah, someone is there, and it will automatically brake the vehicles. Means you can avoid the accident or abnormalities if there is ADAS in the system. So similarly, we can correlate H infinity control with this. So ADAS is nothing but they are using H infinity control only. So what is H infinity control? Means if there is any control plant, like vehicles only, if there is some abnormal thing is happening, suddenly abnormal thing is happening, which human may not be able to detect, but that system can detect and they can take a proper action so that casualties or abnormalities can avoid. So here we are again going to learn H infinity control. So what is H infinity control? So H infinity control's aim is to design the controller which can handle these some uncertainties which are happening across the plant, across the systems, or some disturbance happening inside the systems also, So if system is having H infinity control technologies, so that system may give robust performance, robust stabilities instead of there is uncertainties or external disturbances. Okay. So these are the like just introduction of H infinity control. So H infinity control we can use for the CISO systems as well as multi-input, multi-output systems, and we will get stable systems and without sacrificing the robustness. So robustness means system performance. Robustness we can define as the system is acting in the normal way, irrespective of noises or uncertainties or external disturbance are coming inside the system. So H infinity controls works in time domain as well as frequency domain. So it provides the robustness in the frequency domain, and it can reject the disturbance in the time domain. So main focus of the H infinity control is to minimize the worst case gain. So worst case gain we will get like when your input is like disturbance and your disturbance which are affecting your output. So there is a gain which is like output upon disturbance. So H infinity control is to design the controller so that that gain or that disturbance, that amplification we can minimize. It ensures the stability and performance across all possible perturbation within a specified uncertainty set. So these are the some advantages of H infinity control which we have seen. So now how H infinity controls came. So like in the early of the 20th century, normal means classical control was proposed, and that classical control was based on the trial and error method like Nyquist plot, Bote plots, and time domain, in which we are using PID controllers. So these controllers can work in the real systems also, but these controllers is complex or difficult to handle uncertainties or non-linearities, etc. So to avoid these types of limitations, modern control technology, modern control theory was came in the control system, which is focused on the state space representation and optimal control techniques. So state space representation means we can represent the plants in the state space model, and then we can control the plant by using digital systems. And if it is in the transfer function, then it is difficult to handle that transfer function by digital system. But if you are converting your system in the state space models, then we can easily handle by using digital system. And then in the other topic in the modern control system is like optimal control. So in the optimal control, there is mostly used technique is LQR and Kalman filters, whichever is developed. The main aim of these controllers technique is to design the controllers so that we will get the optimum performance by the system. So however, these methods is also unable to handle the uncertainties or disturbance which are coming inside the system. So in the 1970s, researchers has become familiar with these limitations, and they started working how we can design the system so that we can design the controller, and then that controller can also works in the system which can handle uncertainties and external disturbances. So researchers like continuous working, and in the 1980, so in the 1980 and 1980-81, H infinity control concepts was came. So what is the meaning of H infinity? So H infinity means it is having two words, H and infinity, which we'll learn later. So the main aim is uh, to maximize the gain of the system across all the frequencies. So here we are going to learn how H infinity control was came into the control system. So in 1981, first like George James has introduced the concept of H infinity in terms of sensitivity minimization. Means he has proposed some techniques to minimize the sensitivity. Sensitivity means like our system will become less sensitive with respect to like noise and disturbance, its uncertainties, etc. So this concept is similar like a H infinity control. And then in 1984, John Dell and Glenn has proposed in the formal like H infinity control problem, which we can solve by using algebra by using like transfer function approach to achieve the robustness, performance, and robust stability. And H infinity control was developed by K. Glover and John Dole, which can be solved by using Riccati's equations. So now we can see what is the meaning of H infinity. So as we can see, H infinity is made by two words, two letters like H and infinity. So what is the meaning of H? So H means Hardy space, which is used to describe the spaces of a stable system in the control theory. And infinity emphasizes the like H infinity norm, which is like worst case scenarios across all frequencies. Means it is the gain which is obtained by worst disturbance implemented in the system. So now Hardy space is what? So Hardy space is like spaces of the complex valued functions which are analytical in the right half of complex S plane. It means that the spaces uh, lying in the right half of S plane, which real part definitely will be greater than 0. So in the Hardy space, there is two control theories. What is that? That is S2 space, the space of square integrable and analytic functions, and H infinity space for the bounded analytic functions. So now we will see what is S2 space and what is H infinity space. So S2 space consists all functions of complex function Fs, which are analytic in the Hardy space, and that must be satisfied like S2 norm of the complex function should be less than the infinity, which is given like in equation 1. And for the stable systems, S2 norm we can calculate by using equations 2, and it is defined like running square roots. So what is the role of H control theory? So H infinity mainly measure the energy of impulse response, and in optimal control, S2 norm is used to minimize the minimum energy or least square performance. And now we can see what is the H infinity space. So again, H infinity space we can define like all the functions that are analytic in the Hardy space C plus and which satisfy the equations 3, means the H infinity norm of the complex function F should be less than the infinity. And for the stable systems, H infinity is nothing but the supremum of the complex function, supremum singular values of the complexity. In the measures the worst case gain of a system, and that which is critical for the robustness of the plant. In H infinity control, the goal is to design the controller that minimizes the H infinity norm of the closed loop transfer function, which ensures the robustness against disturbance and uncertainty. So now which is in the next slide. So now we have seen that is used for like transfer functions. Again, here we are going to learn like L2 norm, which is the like nothing but the energy of signal or function, and it is defined by equation 5. So it is like mod of 2 mod of signal function, and which is nothing but the square roots of the integration of square of the function. Or in the frequency domain, we can also determine the L2 norm of function f by using equation 6, and which represents the total energy of signal or any function. So in the control theory, we can use L2 norm to measure the energy of a system's impulse response or the energy of a disturbance. So L infinity norms measures the peak amplitude or maximum amplitude of a signal or function. For a function ft defined on the time domain, L infinity norm we can define by equation 7. It is nothing but the supremum value of ft. For a function, okay, just I have to stop video. So L infinity norms in the control theory is used to measure the maximum gain of the system in the frequency domain, which is critical for the robustness analysis. So in the H infinity norm we are using in the closed loop system. So closed loop system is the system which is having like a forward path and close feedback path. So in the closed loop there are like three blocks. One is like plant, which is the plant which is the which we will control, and then controller which is used to manipulate the control input, and then feedback. Feedback is the path by which we will fed output into the input side. And the plant of the closed loop system, we can get equation 9. So this is the like now we are going to implement our S infinity control in the general plant. So before implementing, first we have to learn what is our general plant. So this is like a general plant in which there is a plant and controller K, in which there is two inputs. One is like input controlled input U, and another one is exogenous input W. That input may be error or reference input or disturbance. And this plant there is also two outputs. One is like Z, which is like known as a error, which we will minimize by using H infinity norm, and then there is a Y, which we will measure to the which we can measure for designing the controller K. And where P and K are the matrices. P means transfer function of the plant, and K is the transfer function of the controller, or transfer matrices of the controller. So now we are going to define the problem statement of H infinity control. So the main goal of the H infinity control is to minimize the closed loop transfer function of the system, which and we have to design the controller so that we can minimize the closed loop transfer function T, and we can also, that K can also stabilize the system internally. For a given plant, which is given like equation 1, 2, and 3, we are going to implement our H infinity control. So, like we have seen in the here, there are two inputs and two outputs. So, the form as given in equation 14. So, the two outputs that is exogenous input, control input U, and U we can measure input U is nothing but K times the output, K times of the output. Here U is nothing but like K times output. Okay. So by putting U is equal to Ky in these equations, we can convert this in the form of this. How we can convert, like here we can write like Z is equal to what, P11W plus P12U, and Y we can write P21W plus P22U. Here U, if we will put U is equal to Ky in this equation and in this equation, then what we can get like Y is equal to what, P21W and then P22 K times Y. So here Y and Y is there, so we can take common. So we will get Y value, and here we have already put U is equal to Ky, so that Y we will keep here. So we will get Z is what? Z is nothing but like P11, P12, and this times W. So what is the use of this? So here we are going to correlate the output error with respect to disturbance input or reference input or uncertainties. So Here we can see the disturbance or reference input or uncertainties are directly related with the error Z. So now we will, before going to design the controller, we have also defined the state space model of controller. So this is the state space model of the controller, and we can write in the matrix on this. So by using this controller, we can write the plant transfer matrices this, and where AK is defined this, BKK is defined this. Similarly, we can define CK and DK by putting this controller matrices in the plant. We will get this. So our objective is to minimize, means we have to get the H infinity norm of the closed loop transfer function T, and that is nothing but the maximum of the maximum of singular values of closed loop transfer function T. The solution of equation 10 R of 10 within, like in the K space means the values of controller lying in the K space, that is K space. So we can get the like unknown parameters of the controller by minimizing the T. T is closed loop transfer function. So where the H infinity norm in 21 is then nothing but like L2 norm operator, and which we can get in equation 22, and it is nothing but this. So by using this, we can determine the closed loop transfer function, closed loop H infinity norm of the closed loop, and this should be less than the gamma, and gamma will be given, and that must be less than 1 for getting a robust stability and robust performance of the plant. So in the previous problem, we have seen like only there is a one exogenous input. So there may be different errors are there. So these are like our objective is to control the disturbance rejection. We have to control the tracking accuracy. We have to control the control efforts. So etc. So there are like three outputs which we want to control or we want to minimize, etc. So here this is the plant. So here we can write like what this is the, we can represent like Z. So it is nothing but this whole block we can write like the transfer function N and then input W. So what is our goal? So our goal is in the previous like diagram, goal is to minimize the controlled plants H infinity now. So where N we can define by using weighted matrix K and complementary sensitivity function Ks, and then weighted matrix T, which is used for tracking, and then P is the complementary sensitivity function, and then we can also minimize the control sensitivity function Ks, which is given here. And here we can see like in the equation 24 we can get by the block diagram. So here from Z what we can get like U times W U Z2 we can get like G times U into WT. So from this like what is the value of Z1, Z2 and Z3. Similarly we can also get what is the value of Y. So Y value, this is the nothing but Y we can get. So it is what it is W, and this is U, that is multiplied by. So here this is the value. So having three outputs which we want to control. So our plant we can write in this term. Okay, and we can use what is the matrix WU, what is the WT, and what is the WU according to our requirements. And then the H infinity norms of that N should be less than the gamma. And what is the complementary sensitivities? So that is our means to limit the control effort in frequency band. We had to increase the weighted matrix WU in the frequency band which is given. So for the minimizing the T at high frequencies, we have to choose WT as a large outside the bandwidth to obtain the small T. we have to also minimize the complementary function S at low frequencies. For good reference tracking and disturbance rejection, we have to choose weighted matrix WP large inside the control bandwidth to obtain the small gain. So now these are the like problem formulation by solving H infinity norm. So we can solve H infinity norm problem either by using equations or by using LMI's approach. So here we are going to how we can solve by using Riccati's equation, and then later we will see by using LMI's approach. So this is nothing but this is our plant, and our motto is to design the controller by minimizing the H infinity norm using Riccati equations. So the goal is given here. So here what is the in the Riccati sequence, this is Riccati equation, everyone is knowing this. So what is our objective in the Riccati equation? So we have to Riccati's equation. Riccati's equation here, A, B, Q, R, which are the known system matrices, and by solving this Riccati's equation, we can get what is the controller matrices K. So here this is the plant numerical plant. We are going to see the numerical solutions of by using H infinity method. So this is the plant in which matrix A, B, and then the C and D are given here. So what is the objective? Objective is to design a controller that minimizes the worst case of the disturbance D on the output. So what is our motto? Our motto is to design the controller so that there will be least effect of disturbance on the output Y. So here we can solve by using like Riccati's equation. So we will assume like U is nothing but K times X, and by solving the Riccati's equation, we will get that X. So Riccati's equation is here given, in which we already know the value of R, value of Q, and we have to find out X value. So here we will assume for solving Riccati's equation, we will assume what is the value of X. It will depend upon the order of A. So order of A is like 2 cross 2. So X order will be like 2 cross 2 only. So here we can solve one by one. So first here we are going to solve like this term, and then we can solve this term, and then we will combine, and we will get what is the value of X. So this is the A transpose, and if you will multiply, then you will get A transpose X this term, and then similarly you can multiply, you will get X a term, and then if you will add it, we will get this term. Similarly, if you will solve this this term, if you will solve this term, you will get this, and then if you will add overall, so you will get what is the value of X. If you will equate with equal to 0, then you will get the value of X. So by using X, we can determine the controller matrix K. So the controller matrix K, this is the obtained by using Riccati's equation, and by using this, we can minimize the effect of disturbance in the output. Now we can also solve the H infinity problems by using LMI's approach. So in the LMI's approach, we had to first construct some constraint based on the requirement. So these are the constraint which we had to minimize by using H infinity norm. So here, what is the motto? So our motto is like system should be stable and disturbance to output gain should be bounded by H infinity norm. So if the LMI is feasible, controller can be derived by ensuring the robust see how we can solve the mathematical problems by using LMI's approach. So these are the plants which is given here, and then this is our control input which we have to find out by using LMI's approach. And what is the motto? Motto is the closed loop transfer function should be less than the gamma value, and gamma will be less than 1. So these are the constraints which we have to solve. By solving these, so you can define the value of X, like in the previous problem we also define the X value, and we will solve this. So we will solve one by one, and then you can get these values, and then you can combine, So if you will combine, you will get finally the values of x and values of y. So y is equal to kx. So we can get what is the value of k, and by using k, we can design our control input u. By using this input, we can minimize the effect of disturbance in the output. So now we can see if you are going to design the controller by using H infinity norm, so what you are compromising. So like in terms of stability and performance, design the controller so we can get robust stability and robust performance in the when there is uncertainties and external disturbance are there in the plant. So robustness means what? Means your controllers is able to handle uncertainty, disturbance, and variations. And stability means our system is stable even though the system is subjected uncertainty, disturbance, etc. So if we are going to design the controller which achieve the better disturbance rejection, so what it can, so it will be more conservative to the controller. So a controller is designed to reject the disturbance from wide range of frequencies. So it may compromise the system performance in lower frequencies or result in higher control effect or larger controller gains. On the opposite side, if we are going to get robust performance, means better reference tracking or reduce the system steady state error, may make more aggressive assumptions. So it will reflect the system behavior which could may create the problem in the robustness when there is uncertainties or disturbance. Similarly, what will be effect in the gain? So H infinity's aim is to balance two important characteristics. What is that? Sensitive function and complementary sensitive function. So sensitivity means what? Which if like system is disturbance or noise, so if it is less sensitivity, so its output will be less sensitive. And complementary sensitivity function means if we will optimize the low complementary sensitivities, so which can improve the tracking, but may reduce the disturbance, especially in high frequency range. So if you are going to do the design the H infinity control in the sensitivities point of views, so it may uh, not provide the good tracking. And if you are going to design for good tracking purpose, maybe your system will become higher sensitive with uncertainties or rejection. So in this context, we can compromise, so maintain the stability when system is subjected uncertainties or external disturbance. And we have to also get robust performance which can reject the disturbance, noise, or modeling inaccuracies. So now we have to see why we are why we are learning H infinity control. What is the key aspects of robustness in the H infinity control? So the key aspects is we have to design the controller so that we can handle the uncertainties. So what is that types uncertainties? Maybe parametric uncertainties, modeling errors, external disturbance, or measurement noise. So in the H infinity control, these are uncertainties are like represented by blocks that can be added in the system's transfer function. So what is the main objective of H infinity control is that we have to minimize the effect of these uncertainties on the system performance, which can be achieved by ensuring the system reject disturbance within the given uncertainty bounds. Now we can see sensitivity and complementary sensitivity function. So in terms of H infinity, so sensitivity means we have already learned what is the sensitivity. So a lower sensitivity indicate that better disturbance rejection, which is the key aspects of the robustness. Means our system is robust, then it will be less sensitive with disturbance or noise or uncertainties. And complementary sensitivity means the function measures the system response, which can track the input in the H infinity control robustness analysis often involve So main goal is like if we are minimizing the sensitivity function S, which can ensure the system sensitivity by minimizing the worst case condition and ensuring that the complementary sensitivity function remains within the acceptable bound to guarantee the performance. Now we can see robust stability in H-infinity control. So in H-infinity control, robust stability and robust performance are the key objectives that is the motto for designing the controller design. So here stability we can check by using like Lyapunov stability theorem or small gain theorem. And by using these, we can also check stabilities by determining the closed loop poles of the system, and this should be lies in the left of a complex S plane. And in the small gain theorems, the and output. So in the norm, the closed loop system is sufficient. Means any model uncertainties and disturbance is not likely to destabilize the system. So uncertainty model. So if there is like uncertainties in the plant, which may be multiplicative uncertainties or additive disturbance, they are represented by uncertainties blocks. The controller must be designed to ensure that the closed loop system remains stable under all the possible variations of these uncertainties. So how we can check the robust stability? So we can check the robust stability by using Lyapunov and in the Lyapunov, if we can get the suitable Lyapunov function, then we can say that yeah, it will ensure the stabilities under some perturbations. If small gain theorem means it can provide the criteria for robust stability, which ensures the overall gain should not be exceed a particular threshold values. And in the frequency domain, we can check the stabilities by using Bode plots or Nyquist plots, which are commonly used in stabilize the stability margins and which verify the robust stability uncertainties. In H infinity control, robust stability and robust performance are achieved through careful design that minimizes the worst case behavior of the system in face of uncertainties and disturbances. So case studies of robustness in H infinity control. So like if we want to control the aircraft, in the aircraft we can see there are so many disturbances in terms of like varying the wind sensor inaccuracies, dynamic changes. So we had to handle that. These challenges is so what is the challenges? We have to design a controller that can handle these uncertainties while ensuring both stable, robust stability and robust performance in tracking and disturbance reduction. So how we can do? So we can design H infinity controller that can work. We minimize the worst case impact of uncertainties on the aircraft performance. And we have to also design the controller which can provide the robust stability. So the controller was designed which can ensure the stable under worst case disturbances by maintaining the desired robust performance of the aircraft. So robust performance, the H infinity controller is minimize the system sensitivity to aerodynamic uncertainties while preserving the excellent disturbance in the rejection. So what is the outcome? So outcome is like H infinity autopilot controller successfully stabilize the aircraft even in the presence of significant external disturbances like turbulence. Robust performance can also be achieved across a particular range by ensuring the aircraft would reject the disturbances such as wind, dust, maintain steady flight with minimal deviation from the desired path. The design of IS Infinity controller ensures the robust against model uncertainties, which is essential for the flight safety in real world applications. So now we can see where we can implement the H infinity control. So H infinity control is now widely used technique in the control system where uncertainties and disturbance are exist. So like we can see individuals where we can see the applications of H infinity. So we can see like in aerospace and automotive engineering. So in the aerospace, it can use to enhance the stability and robust performance against the uncertainties, sensor noise, and turbulence. It can also be used in missile guidance system to improve the trajectory tracking and disturbance rejection. In automatic control, it can be used to adaptive cruise control, lane keeping systems, and vehicle stability control. In H infinity control can also be used in robotics and mechatronics. In the robotics, it can use for precise motion of control under dynamic uncertainties. In the power system and electrical system also we can use H infinity control, like in the power grid stability we can use our frequency and voltage control. In the smart grid and in the motor we can use to enhance the robustness in servo and induction motor control. And in the process control we can use H infinity control to maintain the desired operating conditions despite of the disturbances. In oil refining and pipelines we can use to control the pressure and flow rate of the liquid. In communication and signal processing, H infinity control is used for filtering the signal, means enhance the speech and audio clarity. In network control system, it can use to improve the stability under communication delays and packet loss. So now we can see comparison of H infinity with other control methods. So other control methods we will focus here, LQR and PID. So H infinity control is focused to design the controller for getting robust performance and or uncertainties. So its focus is to minimize the worst case gain of a system, and that gain is obtained when disturbance is as an input. So LQR, in LQR technique, which is focused to get the optimum performance by minimizing the cost of the function by balancing the state deviation and control effort. PID control, it is a simple and widely used feedback control that corrects the error which is based on the residual values. So now we will see what is the comparison in terms of handling the uncertainties and robustness. So the model uncertainties and external disturbances by making it robust against parameter variation and unmodeled dynamics. LQR, so LQR can accurate assume the accurate model and does not handle the uncertainties. It provides optimal performance only for the nominal system. PID controller is not respect to some uncertainties. PID control works well on many practical applications, but it is struggling for nonlinear and time delay systems. So for like fourth point, we can compare H infinity control with other computational complexity. So no doubt, H infinity control algebraic Riccati equations. PID controller is one of the simplest technique to implement the controller. And in PASA view, we can use H infinity control in the aerospace robotics uncertain systems where robustness is more critical. LQR we can use in trajectory optimization, economic models, and process control where the system it provides the superior rejection of disturbance. It can easily handle the multiple input and multiple output systems. Even though it can handle single CISO also, but it can also handle MIMO. It can also accurate model of the plant. It is difficult to tuning and implementation for system. It always practical applications. It may lead to over conservative designs. So now we can see where recently HNPT control are using. So HNPT control is also extended for the nonlinear systems by using Hamilton-Jacobi's Isaacs equations. It also involves it can also use to solve the nonlinear problems by using machine learning and dynamic programming. H-infinity control is also used in the model predictive control, which combines the H-infinity control to handle constraint. It allows in the model predictive control to get the robust trajectory optimization while considering the system. So exact H infinity optimal controls may be difficult to implement in the practical applications due to computational complexity or limitation. Therefore, suboptimal H controls seek the controller inequalities problem, which can be solved by using convex optimization technique. H infinity control and performance can implement the multi-agent system. So H infinity control methodologies can be extended to the MA where you ensure the robust performance across the networks of interconnected agents. This includes managing disturbances and uncertainties at the and modeling errors. Controls are multi-objective functions. So advanced H infinity control problems may involve in the multiple performance objective function that must be balanced simultaneously. This could also include meeting H infinity control problem is LMIs, which can be formulated as a problem of the H infinity performance.
Thank you, Dr. Prajapati, for delivering such a nice talk. So, participants, if you have any doubt, you can ask Dr.
No
Prajapati.
one is having doubts. Anyone who is having doubts? Happen frequently, which so as I have given like in the systems, so ADAS system is also examples of H infinity control only. So ADAS is designed to handle the means unpredictable. Then ADAS controls can also work where cost is not means where life are more critical, like in the flight where we had to use edge infinity control so that we can handle the uncertainties which are caused uh, uh, due to any reason. Okay, so these are my summaries. So thank you, everyone.
Thank you, Dr. Prajapati. So, if anyone has any doubt, you can email him about this H-infinity-based robust control. And our next talk will be on fundamentals of cyber physical systems and its application from A to Tech. So it will start at 3:30. So we can wait for 5 minutes, and we'll wait to join Mr. Prakaski from A to Tech. So he will deliver the talk, and we can hope for some real-time applications. Okay. So this will start at 3:30.
Dr. Sauradeep,
Yes. Yes, sir.
may I request you to please again announce the evaluations that we are going to conduct tomorrow uh, to the participants?
Yes, sure. So tomorrow there will be a quiz at 7 p.m. and syllabus will be up to day 4. Okay, so all the lectures and PPTs have been shared over email to all the participants, and it is mandatory for all the participants to participate in that quiz. If you actually have participate in the quiz, then only the certificates will be issued and the credits will be given. Without the quiz, it will be, yeah, I mean, that certificates will not be issued. So this is mandatory for this particular GAN course on uh, resilient control of CPS. So I request every participant to please join in the quiz. So, and please remember the time is tomorrow at 7 p.m. If you have any doubt, you can ask me or you can email me also.
It is just for the sake of informations that the PPTs of today's morning sessions are shared with all the participants. And the PPTs of the afternoon sessions will be shared in the evening. Student volunteers, please make sure that the recording will still on, remain on during the discussions.
Uh, our next presentation will be on fundamentals of cyber physical system and its application. I welcome Mr. Prakash K from EduTech. Uh, am I audible, Mr. Prakash K? Mr. Prakash K, am I audible?
Dr. Sauradeep, I just got a call from their end. He is going to join. So we can wait for 1 or 2 minutes. And if the participants have any queries related to the previous sessions, then I guess Dr. Prajapati is also here. So we can try to answer those queries. Dr. Sauradeep, Mr. Prakash has joined the meeting. Can you coordinate the session, please?
Sure, Dr. So welcome, Mr. Prakash K. Today we'll have a lecture on fundamentals of cyber physical system and its